Dear students, welcome to the lecture number 8. So today we shall prove the famous theorem, in fact it is called lemma, called Urysohn lemma. Actually the proof of this lemma is very larger than the usual one, but the proof is very interesting and it uses very fundamental theories. So it will be very useful. So let's see the statement first. So let X be a normal topological space and let A and B be two disjoint closed sets, say subsets of X. Now then there exists a continuous function if from this x to 0, 1 such that so f of a equal to 0 for all a belongs to that set capital A, and f of b equal to 1 for all b belongs to the set B. Okay, so now we shall prove this theorem. So here is the proof. So as I mentioned that the proof is very fundamental, so you have to be very careful reading this proof. So first of all, we denote Q by the set of rational number, right? You know that. So we just recall that. So recall that Q denotes the set of rational numbers. Okay, now we say for any subset R, subset of Q, that is R is a subset of Q. Okay, we say that subset R satisfies a property, or you can say the properties star if for any 2 point, so for any 2 point P comma Q belongs to that set R, there exist open sets with the index P and Q. Okay, this means U P and U Q such that U P closure subset of U Q. Fine, that's mean Q is a set of rational number. Now suppose R is a subset of Q. R can be a finite subset of Q, it can be an infinite subset of Q, it can be the whole Q, right? It is just a subset of Q. Now we say that subset A, R, satisfies the property star if we choose any two pair of point P and Q from R, then we will have two open sets UP and UQ such that UP closure subset of UQ. Okay, we will use this fact. Now we back to our main problem. So it is given that A and B be two disjoint closed sets in X, right? Okay. Now given A and B are two disjoint closed sets in X. Okay. Now let U1 equal to X minus B. Okay. That's mean U1 is an open set which is the complement of B. Right. That is A subset of U1 where A is closed and U1 is open in X. Right? Now it is given that X, that is the topological space X, is normal. Now from this, what can you say about this pair A and U? See, if you remember that in the last lecture we have proved that if we have any pair of an open set and a closed set, that is A subset of U1 where A is closed and U1 is open, then we have another open set, say V, such that A subset of V and V closure subset of U1, right? But here we will choose the set U0, not the V. Now since X is normal, so there exists an open set, say U0, such that A subset of U0 and U0 subset of U1, that is U0 closure subset of U1. Right? Why? It is by a previous result. Right? Okay. Note that here we get two rational numbers 0 and 1, and we have this property, that is U0 closure subset of U1. Right? See this property, right? That's mean if we choose my R equal to only 0 and 1 this set, then this property satisfied, right? Now we get an idea. What are the idea? So we can find a collection of rational number, that is a sets of rational number with the first two entries 0 and 1. Okay, let's do this first. Now let P be the set of all rational number in the closed interval 0 and 1. Right? We know it is countable, right? Now since P, that is the set P, is countable, we can write P as P equal to say x1, x2, x3, x4 in this way, right? Fine. Now, do you know that how to count the rational numbers? So that's mean we know the set of all rational number between that 0 and 1 is countable. So we can write it is in this way, right? x1, x2, x3, x4. Now can you give a value of this x1, x2, x3, x4? Of course we can give, right? So we can say so let x1 equal to say 0, say x1 equal to 1, right? We can write x3 equal to half. Then we can write my x4 equal to 1 by 3 and x5 equal to 2 by 3, right? We can write then x6 equal to come to the 4, that is 1 by 4, and x7 equal to 3 by 4 in this way, right? Similarly, we can write x8 equal to 1 by 5, x9 equal to 2 by 5, right? Then x10 equal to 3 by 5, x11 equal to say 4 by 5, then again x12 equal to 1 by 6 in this way, right? In this way we can enumerate all the rational numbers between 0 and 1 with the first entry 0 and 1. Fine. So why I am doing that? Because I want to prove that the set P, which is the subset of Q, satisfies the property star. That's mean if you choose any 2 points P and Q from P, then UP closure subset of UQ, right? So I want to prove that. So that is my focus point. But in general, it is difficult to see that property is true. Therefore, I want to prove that property by induction. So that is the reason I choose P in this way and let Pn equal to this set. Fine. Now see, we have already seen that U0 closure subset of U1, right? And x1 equal to 0, x2 equal to 1. Therefore, P2 is true, right? Therefore, P2 satisfies the property star. Now, before going to the induction, we just write the statement. So, let Sn be the statement that Pn satisfies the property star. That is, for any P, Q belongs to Pn, there exist open sets UP and UQ such that UP closure subset of UQ. Okay. Now we have already proved that S2 is true, right? Now here is my base case. So my base case of the induction is n equal to 2. Now since U0 closure subset of U1, that implies S2 is true. Okay. Now to prove the induction, we need to assume that Sn is true for n equal to k, and we need to prove that that is true for n equal to k plus 1. But before going to that, I want to do some unnecessary step to understand the clear picture. Okay, so you can skip this part. So first of all, it is given that U0 closure subset of U1 where U0 closure is closed and U1 is open. Right? Now since X is normal, so there exist open sets. We say that open set is my U half. Why it is my U half? You can see that my third point, that is x3, is half. Right? You can check that x3 is half. That is the reason we choose U half. Or U half such that U0 closure subset of U half and U half closure subset of U1. Right? Therefore, S3 is true. Right? Now similarly, you can prove that S4 is true, S5 is true, S6 is true, everything is true. Right? But anyway, this is not a mathematical proof. But we have to give a mathematical proof, right? So that is the reason we are giving that induction. So this is just a part to understand that one. Okay. Now come to the main proof. So let Sn is true for n equal to k. That is pk satisfies the property star. Right? In other words, that is for any 2 points P and Q belongs to PK, there exist UP, or you can write there exist open sets UP and UQ such that UP closure subset of UQ. Okay, now we prove that then Sk plus 1 is also true. Now consider the set P k plus 1. Now we need to prove that Sn is true for n equal to k plus 1. That is, we will prove that Pk plus 1 satisfies the property star. Okay. So what is my Pk plus 1? It is Pk. So Pk plus 1 equal to my Pk union the set, the singleton set x k plus 1, right? Just rename that point. Say this is my R. So let x k plus 1 equal to R. So it is up to you that you want to rename this x plus 1 by r or not. Here I am renaming this point as r because I need the set u suffix r. So if I do not rename this, then I will have the open set u suffix x k plus 1, which looks difficult, right? That is the reason I am renaming this set. Anyway, so what is my pk plus 1? So here pk plus 1 is a finite set in 0 1, right? And r not equal to 0 and 1. Now therefore the point r will have an immediate predecessor and immediate successor. So first of all, therefore r has an immediate predecessor and an immediate successor in pk plus 1. So let p be the immediate predecessor and q be the immediate successor in pk plus 1. So we can write of r in pk plus 1, right? Therefore p comma q belongs to pk and p less than k, right? Now I just want to make one correction which I missed that. So whenever I choose two element p and q, we should have p less than q. So go to the back. What is my property star? Here, right? So for any pq belongs to r with p less than q. So this is my property. So if we have any 2 point p and q from a finite set, then, or for any set, then there exists open set up and uq such that up closure subset of uq. That's mean this is my base case is clear, right? And this is my pk again here. So with p less than q. This. Fine. Okay. Now since sk is true, so therefore there exist open sets up closure subset of uq. Fine. And where is my r? Now again up closure is closed and uq is open in X and X is normal, so there exists open set, say UR, such that UP closure subset of UR and UR closure subset of UQ. Now we prove that PK plus 1 satisfies the property star. So choose any two elements from PK plus 1. So choose any two elements from PK plus 1. Now there are three cases. Now if the two elements are elements of PK, then we are done, right? Because PK satisfies the property star. So if we choose any two element from PK plus 1, now there is one case, it may be that 2 points belong to PK, then that satisfies the given, that is the required property. So we are done. Now case 2, so let one element is R and another element is S, which is less than equal to P. Okay, so why this is true? Because see, it is given that, so we have proved actually, so P less than R less than Q, right? And we have chosen two elements from PK plus 1. Now if the two elements are in PK, then we are done. That was in the case 1. Now if the two elements are not in PK, that's mean one element is R and the other element will be in PK. So let the other element is S. Now there are two cases. It may happen that S less than equal to P, and the other case is S is bigger equal to Q, since P less than R less than Q, right? Now this is my case. So S less than equal to P. Then US closure subset of UP. Why? Because S is element of P, right? So it is true if S is less than P and US equal to UP, otherwise, right? In any case, we can say that US closure subset of UP closure for S less than equal to P, right? But we know that UP closure subset of UR. Now that implies US closure subset of UR. So we are done, right? That is the property satisfied. Now my case 2. Next case, case 3. So let one element is R and another element is S, which is bigger equal to Q. Now again, then we can say that U Q closure subset of US if Q less than S, and therefore we can say that UQ, which is just subset of UQ closure subset of US if Q less than S, and if Q equal to S, then UQ and US are actually same, right? So therefore we can write, so UQ subset of US if Q less than equal to S. Further, we already have, see, we already have a between R and Q, that relation, right? UR closure subset of UQ, right? UR closure subset of UQ. That imply UR closure subset of UQ subset of US. That is UR closure subset of US. So we are done. That's mean we have chosen two elements from k plus 1, and if the two elements is one less than other, then we have proved that one, that is the lower one's closure, is subset of the that is contained in the other open sets, right? That imply, so thus we can say that K plus 1 satisfies the property star. That is, S K plus 1 is true. Therefore, by the mathematical induction, we can say that Sn is true for any n. So, thus, by the principle of mathematical induction, we have Sn is true for all n, right? Okay. Now here I claim that the set P satisfies the property star. See, what is my P? P is just union of P1, P2, P3 and in this way, right? See, now P1 satisfies a property, P2 satisfies a property, right? And by the mathematical induction, we know that Pn satisfies the property for all n. But that does not mean that their union also satisfies the same property. But here, in this case, that will be true. Because, so let P, what is my P? So P is the set of all rational number between 0 and 1, right? Now let any two element, say small pq, belongs to my capital P, right? Then there exists natural number n such that that point PQ belongs to that set Pn. Now we know that, so here, so let P less than Q, right? PQ belongs to Pn. Now since Pn satisfies the property star, therefore UP closure subset of UQ, right? Now since the pair P and Q are arbitrary, therefore the set P also satisfies the property star. That's mean for any 2 point P comma Q belongs to that set P with P less than Q, there exist open sets UP and UQ such that UP closure subset of UQ. Note that, so I just again just diverge from this direction. I just want to make one note that if some property is true for all n, then that property may not be true for the union. But here this is true because that property is not the global property. So I can give you one example that is not true in general. So let say A1 equal to my set, say 1 by n, comma, say 3 minus 1 by n. That is set, right? Now, say this is my an, right? Then each an is a closed set. That's mean A1 is closed, A2 is closed, and this is closed for all n, right? But if you take union n equal to 1 to infinity an, this is just the set open interval 0, 3, right? Is not closed. Therefore, each set satisfies some property. That does not mean that even there, these are the sets, one contained other, right? So any collection of sets, each of them satisfies a certain property. That does not mean that their union will satisfy that property. But here we prove that each of Pn satisfies a property that will imply that the set P, that is their union, is also satisfying that property. So this does not come from the mathematical induction. So we proved here. That is the reason we proved this claim. Since the property depends only any two numbers, so this is true. If there is a property which is a global property like a open set or closed set which is a global property, right? So that kind of property may not be true for the union as well. Now back to the main problem again. So here we prove that the set P, which is the set of all rational numbers between 0 and 1, satisfies the property star, right? Now I want to extend this property from P to the set of rational number Q. So just define, so first of all let P be any number, that is any rational number in R. Now define UP equal to just empty set if P is less than 0 and UP equal to whole set X if P is bigger than 1. Now obviously UP closure is equal to UP itself in these two cases, right? So it is easy to check that the set Q satisfies the property star with this chosen UP, right? Now define, so for a point X in X, define the set QX equal to all of this collection of all of this rational number P such that X belongs to UP. Okay. Now from this construction, can you give one lower bound for QX? See, if UP is non-empty, then P should be bigger or equal to 0, right? So we can say that if UP is non-empty, then P should be greater or equal to 0, right? So that implies 0 is n, or you can use a lower bound for QX. Also, if P is bigger than 1, that implies UP is X, right? So UP contains all the elements of X, right? Therefore, for any X, QX contains all the rational numbers greater than 1, right? Why? Because see, what is my QX? QX is all such rational number P such that X belongs to UP, right? Now if P is bigger than 1, then UP is capital X. That means X should be in that element. Therefore that index P will be in QX, right? Therefore QX contains all the rational number greater than 1, right? Now if we define a function fx in this way, it is infimum of all such P such that X belongs to UP, this one, right? Now this is well defined. Because why this is well defined? Because what is this set? This set is just UX, right? So this is just QX, and we know that this set has a lower bound. What is that lower bound? It is 0. We have proved that, right? 0 is a lower bound for QX. Therefore, this set has a lower bound, right? So infimum exists. And also, since the infimum exists and 0 is a lower bound, therefore we can say that fx bigger equal to 0, right? Because 0 is a lower bound for qx and fx is the infimum of that. Infimum means the greatest lower bound. So 0 is a lower bound and fx is the greatest lower bound. So fx is greater equal to 0. And also from the fact that qx, now since qx contains all the rational numbers greater than 1, therefore if we take fx, that is infimum of this one, should be less than equal to 1. So fx, which is just infimum of this, should be, it is less than equal to 1. Why this is less than equal to 1? Because this collection, that is this qx, contains all the element, that is all the rational numbers greater than 1, right? So that infimum can be at most 1. So it cannot be more than 1, right? Okay. Now this part is done. Therefore, we can say 0 less than equal to f of x less than equal to 1. So fx is a function from x to r and its image, that is the range of f, is just closed interval 0, 1. Thus f x to r is a function and 0 less than equal to f of x less than equal to 1. Now we claim that f of a is singleton 0 and f of a is singleton 1. Why f of a is singleton 0? This is also simple. So let x belongs to a, right? Now by the construction we have seen that a subset of u0, right? And also that u0, we know that u0 closure subset of up if p is bigger than 0, right? And so this is, you can say just up for all p bigger than equal to 0, right? Thus if x belongs to a, then that qx, that is the set of the rational number, right, for which rational number p for which x belongs to xp is just the set 0 infinity intersection q. Now what is my fx then? Then fx equal to that infimum of this set qx, right? So it is just 0, right? So if x belongs to a, then fx equal to 0. Now we move to the second portion, that is fa equal to 1. Sorry, fb equal to 1. Now why fb equal to 1? Now again, so let again y belongs to b. Now what is my b? b equal to x minus u1, right? By our construction, so we constructed u1 equal to x minus b, that is b complement, so b is u1 complement, right? Now that's mean if y belongs to b, then y does not belongs to u1, right? But we know that for any p less than 1, up closure subset of u1, right? So that implies y does not belong to up as well for all p less than 1, right? That's mean if x belongs to b, then y not belongs to up for all p less than equal to 1, right? So that is y not belongs to up for all p less than equal to 1. But what if p is bigger than 1? But for p bigger than 1, up is just the whole set x, right? That implies x belongs to that point, y belongs to up. So qy is just the collection of all the rational numbers, right, bigger than 1. So f of y equal to infimum of this set is just 1, right? So we are done. So that implies f of a is singleton 0 and f of b is singleton 1. Done. Now the only thing is we need to prove that f is continuous, right? Also we have found that range of f is close to interval 0, 1. Now we claim f is continuous. So claim f is continuous. Okay, so to prove this continuity we need two more results, actually two more observations actually. This is the easy observation. So first one is x belongs to ur closure will imply f of x less than equal to r, and the second observation is x not belongs to ur will imply f of x bigger equal to r. Okay, actually this is the very easy consequence of the construction. First of all, note that if a subset of b in that real line R, then infimum of b less than equal to infimum of a, right? Because this is my real line. Suppose this is my a, say this is my a, and b contains a, right? So this will be my b. Therefore here the infimum is this one of a and infimum of b will be this one. So infimum of b will be less than equal to infimum of a, right? Now we will use this fact only. Okay, now proof. So if x belongs to ur closure, then x belongs to us for s bigger than r, right? Why? Because ur closure subset of us for every s bigger than r, right? Now that will imply if s is bigger than r, then qx contain that s, right? Therefore that set, that is open interval, not open, here it is closed, right? It is belongs to this as well. Okay, no, x belongs to ur closure, but that does not imply x belongs to ur, right? So we cannot write here closed interval. So that's mean r infinity intersection q, that is subset of my qx, right? That's mean qx contains all the rational number which is bigger than r, right? This, now that imply infimum of qx is less than equal to infimum of that set or infinity intersection q. That imply, now this is my f of x and this is my r, right? So f of x less than equal to r. So we are done. Now move to the second one. Again, now if x not belongs to ur, right? Now what is my ur? So we know that us closure subset of ur, right, for all s less than r, right? Now if x not belongs to ur, that's mean x not belongs to us as well for all s less than r, right? That's mean qx does not contain any rational number which is less than r, right? Or you can say less than equal to r, in fact, because x not belongs to ur as well. Now that imply that qx is properly subset as, it may be improper but it may be equal, it is subset A of r infinity intersection q, right? Now that imply infimum of that set r infinity intersection q is less than equal to infimum of qx. That imply r less than equal to qx, sorry, fx. That imply f of x bigger equal to r. So we are done, right? Now from this 1 and 2 we can give one contrapositive argument as well, right? What are the contrapositive argument? So that implies, so we can write these also imply, number 3 we can write, so f of x bigger than r imply x does not belong to ur closure. It is just the contrapositive argument of the first one, right? And 4, that is if f of x less than r, that imply x belongs to ur. Fine. Now we shall use these 4 results, so these 2 and these two to prove that f is continuous. So given a point, say any arbitrary point z in X, and given an open interval C, D containing Fz we want to find an open set U containing Z such that f of U subset of C, D. Right? So this is the definition of continuity. That's mean we have a space X and we have a function f from X to R. Right? In fact, the range is 0, 1. Anyway, we can consider the function f from X to R. Right? Now, we have to prove that this is continuous. Continuous means we need to prove that it is continuous at every point Z. Now say this is my Z. So this is my suppose f of Z. Now to prove the continuity of this function, it is to prove that the function is continuous at Z, we first choose one open neighborhood C, D containing Fz, right? Now we want to find one open set U here such that that U goes to here. That is f of U subset of C, D. Fine. Okay. So here C less than f of Z less than D, where C, D are real number, right? So where C and D are real numbers. Now what we will choose? So we will choose two rational numbers P and Q such that, so we choose two rational numbers P and Q such that C less than P less than f of Z less than Q less than D. Okay. Now let U equal to UQ minus UP closure. Why I am choosing that? So this is a trick to prove that one. So you will understand why I am choosing this set, right? Now obviously U is an open set. Now I claim that U is my required open set. That's mean we need to check two things, right? So we claim that so Z belongs to U. We do not know that, right? And f of U subset of C, D. So we claim these two. So if we can prove these two, that's mean we are done, right? So given we have a point Z and a open set containing Fz, that is CD, we are finding one open set U containing Z such that f of U subset of CD. That will prove the continuity of function at a point Z. Now since Z is arbitrary, so we can say that f is continuous on whole X, right? So we need to only find, so we have already found that U, so we need to only check that Z belongs to U and f of U subset of CD. So first one, so why Z belongs to U? Now it is given that, so by our construction, f of Z less than Q, right? Now if f of Z less than Q, so we have some criteria. So we can go there, see here. So now by 4 we know that, see, f of X less than R imply X belongs to UR, right? So here f of Z less than Q imply Z belongs to UQ by 4, right? Again we have f of Z, see, we can have again f of Z bigger than P, right? Again f of Z bigger than P. Now again by we will use 3, see, here f of X bigger than R will imply X does not belong to UR closure. Now here we have f of Z bigger than P, that's mean Z does not belong to UP closure. Z does not belong to UP closure, it is by 3. Now that imply Z belongs to UP minus, sorry, it is UQ minus UP closure, which is my U. So first property is done, right? So this part is done. Now we need to check this part. So f of U subset of CD. Okay. Now this is the another part. So let X belongs to U. Okay. Now that implies X belongs to, what is my U? That is UQ minus UP closure. Now that implies X belongs to UQ. Now if X belongs to UQ, which is subset of UQ closure, right? Now if X belongs to UQ closure, then we know something, right? We know this, right? So here my X belongs to UQ closure, right? So X belongs to UQ closure, so f of X less than equal to Q, right? Now that implies f of X less than equal to Q, it is by 1, right? Again X belongs to UQ minus UP closure imply X does not belong to UP closure. Now that implies X does not belong to UP as well, right? Now if X not belongs to UP, then from 2 we know that f of X bigger than equal to P. Do you want to check? Okay. So go there, where it is, this is my 2, right? So if x not belongs to UR, then f of x bigger equal to R. Now in our case, x not belongs to UP, so f of x bigger equal to P. So that imply f of x bigger equal to P, right? That imply f of x belongs to P, Q, right? Which is subset of C, D. That imply we choose any arbitrary point, right? Here my x, here this x is arbitrary, right? Here this x is arbitrary, right? Now since x is arbitrary from U and we get f of x subset of CD, that imply f of U subset of CD, right? So we are done. So that imply f is continuous at Z. Now since Z is arbitrary, so f is continuous on X. So thus we get, therefore we get a continuous function f from X to R, right, such that, so range of f is just my 0, 1 and f of A is my 0, f of B is just my singleton set 1. Now since the f is continuous and range is just 0, 1, so we can consider this function from X to 0, 1, right? So thus we have a continuous function f from X to 0, 1. So if you don't like f, then you can just rename it as some f dash or f bar something, but there is no harm if we write f only, because we are just restricting that that codomain, right? Such that f of A equal to 0 for all A belongs to A, and f of B equal to 1 for all B belongs to B. So we are done.